So what we had was speed times the derivative of the unit tangent, okay? And we want this to somehow match up with an a sub n hat times the n hat, the normal, okay? So how do we get this? So the normal vector, the unit normal is formed by taking the derivative of the unit tangent vector, so something like that, right? And then dividing it by the magnitude of the top vector. Okay, so another way to write this would then be to multiply the magnitude times each side, multiply this to this side. Okay, so that's going to be the magnitude of the unit tangent times the normal, okay, of t. And then this, we've already learned that could be rewritten as v of t times the curvature. Okay, so that's how we got that on the previous slide. So we're going to plug this in for the t hat prime of t. Okay, so this is going to be continuing here. So we have v of t times v of t times curvature of t, and then the unit normal of t. Okay, so if we're comparing this with a sub n hat with an n hat, like multiplied together, so we want this to be similar, we want this here to be similar to this, so we can pull out this normal vector, right? The unit normal are the same, so whatever is left over up here must compose the coefficient for the unit normal, okay? So that means that our unit normal is the same as the unit normal, okay, so that's exactly the same, and then our coefficient is now v of t squared times curvature of t. Okay? So altogether, let's write this, what we found out. So we have that our acceleration vector, can be broken down into v prime of t times t hat, okay? And then plus v of t squared times the curvature times the normal vector, the unit normal, okay? And now we know that this part here, the v prime of t, is our tangential coefficient, okay? And then we know that this part here, those three terms, that's our normal coefficient, the coefficient for our unit normal, okay? So a sub t hat, this is the tangential component of acceleration. And I'll just tell you that, so acceleration, and it describes the rate at which the speed changes, okay? So it tells you the rate at which the speed changes, okay? And on the other hand, our a sub n hat here, this is the normal component, so normal, and I'll abbreviate component of acceleration, and this describes the change in the velocity vector. So it describes change in velocity vector due to the change in direction. Because remember the unit normal, or just the normal vector in general, anything that's normal to a curve, well, the normal in this case, this points inward to the curve, and it tells you which way it is bending, right? So how, like, in which direction it is changing, okay? All right, so that's more of a background on the a sub t and a sub n. All right, so now if we look at it, let's try another one again. Sorry. So let's say this is our acceleration vector, okay? It's pointing up and to the right this time. And here's our unit tangent, let's say. And here's our unit normal, like that. Okay, so what are we going to do now? I'm just going to give you a little bit more insight on what's what here. So a sub t hat times t hat is actually a projection, I'll just spell it out here, of the acceleration vector onto t hat, okay? So what that means is that what we have is, like, if you were to draw a perpendicular line down to where t hat is pointing, this thing here, this long vector now, that is going to be your a sub t hat times t hat. Okay? And what that means is that t hat provides the direction, right? And a sub t hat must provide the length, then, the component part. Okay? So if we write it out piece by piece, what we get is that this is equal to a dotted with t hat, and then times another t hat. So this thing here, you compute the dot product once. This is kind of like when like when you project things. Basically, you dot that vector with the unit vector of the direction vector, and then you do times the unit vector pointing in the direction you want it to go again. So anyways, this is the component part. This is the scalar portion. So this tells you, this is your coefficient. Okay, so this is how long it is, right? Because our unit vector doesn't give us any length, right? It just has a length of 1, so when you multiply it doesn't really contribute at all. This does not contribute length. This is your length right here. This contributes direction. Okay, alright, and then another way to rewrite this, if we're going to continue on, so our a sub t hat, is going to be a dotted with, and then we have v, so that's going to be our velocity vector, and then we have another v dot v on the bottom. Okay, and the way we got that was, here's our middle step. So, sorry, I skipped over like a little middle step there. This would be a dot v, and then another v, but on the bottom we had like the magnitude of v, 2 of those. And remember how this is equal to this. We learned this in the dot product section, I believe. Okay, so anyways, so this is just another way to write it. This is showing you that the a sub t times t hat is a projection of a onto t. Alright, so that's what you get there. And then, likewise, we kind of have the same thing going on with the normal. But since that's a little bit more difficult, what we usually do is work with the tangent vector first, everything in the tangential direction. Okay, and then we kind of just like fill in the gaps with the normal stuff. So if we have this, then that means that so this is going to be this long one here. So this big vector is going to be a sub n hat times n hat. Okay, so that's going to be the this component here plus this component. So plus this component here is going to equal the vector that we started off with, right? Our big diagonal one. But if you want to just rearrange it and you want to just solve for this, then you just subtract the tangential stuff over to the right side. So we're going to subtract this, okay, that turns into 0. So then a sub n hat times n hat is going to equal our original acceleration vector minus a sub t hat times t hat. Okay, so here it's kind of more or less like not a process of elimination, but we're just going to move things around once we find out more information about the tangential component, and then we'll use that information that we find out to solve for the normal components there. Okay, and then another way to write this, if we're going to go a step further, more component-wise, is going to be that our acceleration vector, minus, and then I'll just copy this down because this is equivalent to the tangential stuff. So we have a dot v, and then v outside, and then we have a v dot v on the bottom. Okay, so again, that's another just like offshoot of another way we could write and solve for the normal components there. Okay, and one last thing I want to mention. So I'm going to redraw this triangle. So we have our acceleration vector, our unit tangent, and then our a sub t hat going down there, and then our normal. So here's our normal vector, and then here is, okay, going across. Sorry, that's supposed to be a dotted line. Did not come out dotted. Okay, there we go. And then this big one here is going to be a sub n hat. Okay, so one thing to note is that on this triangle, so let's say I just draw one triangle. Okay, I'm gonna move the normal one over here. So this is a sub n hat. and then that one's pointing up there, and then A is over here. I'll actually draw that by the hypotenuse, okay? And then this one is our A sub t, t hat. Okay, so one thing to note is just that because our tangent and our normal, those unit vectors, since they are unit vectors, that means they have length of 1. So they contribute not at all to the length, really, because we're multiplying here. So the length of this side, for example, along the bottom here, if we take the magnitude, what's going to happen is that we don't really, we have this, and then separately we have the magnitude of the unit vector, but this is just going to be 1. So basically, the magnitude of this whole entire side is based on the coefficient, on the tangential coefficient, okay? And likewise with this side. So if we do the same thing, we take the magnitude, then the n hat here doesn't contribute at all. So that just kind of goes away, and we're left with the normal coefficient. Okay, so we can kind of think, and of course, what's it called? The hypotenuse. Woo. Okay, the hypotenuse here that has a length of the magnitude of a. Yeah. So usually you're given the a to decompose, so that won't be that big of an issue. So, anyways, something to keep in mind is that this is that length, and this is the bottom length, and this is the side length. So you can always write, make use of like the Pythagorean theorem or something, and say that like a n hat squared is equal to well, we could do it the other way too, but the magnitude of a squared minus the magnitude, or just a t hat squared. Okay, so this is more or less like an a squared plus b squared equals c squared, but just like rearranged a little bit, like a squared equals c squared minus b squared. That kind of idea. And then if you want to solve for the normal component there, the normal coefficient, you would just take the square root. Okay, so these are just, I'm kind of throwing out formulas here and relations that you could use to solve for certain things when you're decomposing the acceleration vector. Okay, so that wraps it up for this video. I hope that helped, and happy studying.